All right, thank you guys for coming today. Today's speaker is Yang-Hui from University of London. He did his undergraduate at Princeton, then part 3 at Cambridge, and then moved on to MIT for his PhD, working on algebraic geometry, and then moved on to UPenn to do Calabi-Yau compactification. And now he's at University of London, and he's a fellow at Merton as well. So please welcome Yang-Hui.
Thank you very much for the introduction. And thank you, Peter, for having me at this really exciting seminar series that meets two very seemingly very different subjects. But of course, I was told that physicists have been doing machine learning long before theoretical physicists have been doing this subject. So I'm very much a newcomer to this game, and I feel very warm that I've been sort of accepted by this machine learning community. So the idea is I will begin with certain things in string theory, because that's my bread and butter, but we will move gradually to a more broad audience. I realize the audience is quite mixed, so I will try to be as general as possible. So let me just begin with just this one slide that really motivated at least my point of view of doing machine learning, which strangely came from string theory. So of course, you read this about in the newspaper. String theory is this 10-dimensional theory of unified theory of quantum gravity, and we don't live in 10 dimensions, we live in 4 dimensions. We have to reproduce this world of galaxies and elementary particles, and we're somehow missing 6 dimensions. Right? So 10-dimension theory of unified everything, and somehow we have to get down to our world of 4-dimensional universes. So we start with the indisputable equation of string theory. This is probably the one equation that everybody agrees with in string theory. The 10 is definitely 4 plus 3 times 2. Right, this is certainly true. And this story sort of began in 1984. Right? So what do I mean by this? I mean, the 10 is the 10 dimensions of unified space and time and of quantum gravity, and we live in the 4. And the extra 6 dimensions has to have some kind of geometrical property. So this is how I got into the game. This theory, originally started in 1984 with this theory of the quadratic string in 1984. And the gauge groups are not so important. And then there was this seminal paper in 1986 by Candelas, Horowitz, Strominger, and Witten. Philip is here, so you can ask him all about it. And the point is that this gauge group of string theory, this E8 gauge group, accommodates the standard model group. The details of this is also not important. But what is important for me is that the 6 extra dimensions was also found not to be an arbitrary manifold. They have to have certain geometrical properties. So what kind of 6, you can't just randomly compactify on 6-dimensional manifolds. So it turns out that this is not just any real 6-dimensional manifold, but a complex threefold. It is further Kähler, it is further Ricci flat, and there are many classes of solutions. But these 3 conditions are the simplest ones. Okay, at this point, I think everybody's gone to sleep, because who thinks about complex Kähler, Ricci flat manifolds? In fact, physicists in 1984 were certainly not talking about such manifolds. Ricci flat maybe because work of GR. So what the hell are these things? Well, it just so happens that mathematicians were thinking about exactly the same problem. This is why I fundamentally, on a philosophical level, believe in string theory. Every single time there's a string revolution, it always hits on just the right mathematics. It's always the right one. I don't know why. I get very, philosophical about this, but I can't speculate about this sort of thing. So let me just give you a very, very concrete problem. This is a problem that goes back to Euler, Gauss, and Riemann, classical mathematics. What are these things? Well, there's this classical result which we might have learned from topology from kindergarten, which is the study of Riemann surfaces. Now, what the hell are these things? Well, they're 2-dimensional real manifolds, so just surfaces. Right? This is a classical result of Riemann and friends, that there is a complete classification of these things. And in fact, this classification falls under a trichotomy. And this is what we're very, very familiar with. If you ask the thing, there's the surface of a sphere, right? There's the surface of a donut, and the surface of higher donuts, right? My daughter loves this one, and I'm trying to get her interested in these ones. She eats this one too much, probably. But the point here is that there is one number, which is called the Euler number, which classifies these surfaces. So it turns out it's exactly 2 minus twice the number of holes. So this is just, it is what it is. And the idea is that these things, this one, everything is a trichotomy of classification. This is positive curvature. This we know from under our undergraduate days. Everything here has negative curvature, and everything here has 0 curvature. So the classification of surfaces fall into this beautiful, 3 tripartite classification scheme. And the idea that I want to emphasize is the Euler number, which is a single integer which characterizes these topologies. In fact, there's a beautiful theorem. The reason I'm introducing this is because I want to, later on, we're actually trying to machine learn this. Okay, so that's why I want to set the terminology. So there's been a lot of work over 200 years since Euler and Gauss and friends. Is that so here there's topology, which characterizes this integer, this Euler number I'm talking about. And then there's the field of algebraic geometry, which tries to reduce this kind of computation to what's known as characteristic classes. And there's the field of differential geometry, which tries to reduce this computation to some integral over some curvature. That's a beautiful integral. And then there's index theorem, which tries to reduce this in terms of some kind of alternating sum. Okay, these are called Betti numbers. The details, again, are not important, but the idea is that, for over 200 years, mathematicians have really understood two-dimensional surfaces very, very well, and we want to do some kind of generalization of this subject. So the take-home message here is that there is this thing called the Betti number, which characterizes this Euler number, and there's a complexified version. So everything we do here is complexified. That's the 3 times 2. We're not just dealing with 6-dimensional real manifolds. We're dealing with 3-dimensional complex manifolds, just like we don't think about these surfaces as 2-dimensional real things, but we think about this as 1-dimensional complex things. But for the complex numbers, it's just the real numbers complexified. So the take-home concept here is the Hodge number. It's some kind of complexified version of the Betti numbers. Okay, so that's the problem that mathematicians have been thinking about. Okay, and then the story goes on. It is extremely difficult to study high-dimensional things. So for several 2-dimensional things, that was classical results of Euler and friends. But once you go into high dimension, it becomes extremely difficult. You can think about, the Poincare conjecture, the Thurston program, all of this in the high-dimensional geometries, and it's very, very hard to understand them. But at least, so that's where the word Kähler comes in. For our class of Kähler manifolds, we have some kind of control over the past 200 years of pure mathematics. So in 1954, there is this famous conjecture of Eugenio-Calabi. You can read it. But untangling this definition would just bore you to death. We won't get into it. But the point is that at least for these Kähler complex manifolds, for this class of manifolds, the mathematicians are probably thinking about, there is some version of this trichotomy, this uniformization theorem, that you can classify something into positive curvature, 0 curvature, and negative curvature. So this was a conjecture, and it took something like 20 to 30 years before Xintun Yao proved this, for which you got the Fields medal. And it was famously an existence proof. Okay, there's no construction. I'll get into a little bit of this later. And at this point, so the rest is history. So Philip Candelas tells me this is a story where Yao and Andy Strominger were either sharing an office or sitting very close to each other at the Institute of Advanced Study in Princeton, and they happened to be talking to each other. A bunch of physicists having reached from this story of compactification in string theory, this very strange class of objects known as Kähler, complex, Ricci flat, adjectives you can impress your friends with in a cocktail situation. And then there is Yao, who has just freshly proved the Calabi conjecture, for which gets the Fields medal. Because this is really central to mathematics, right? It's not some random theorem. And they happen to be neighbors, and they so Strominger and Philip and say, well, what are these things? And Yao says, well, these are these things that I just studied. And in his honor, these things actually became known as Calabi-Yau manifolds. So that's the word that I want to. So this is going to be our play field. So at this point, you can forget about the physics at some level. At this point, you can go to what Philip describes as card-carrying mathematicians. I don't know who carries, I don't know, visiting cards, I don't know, college cards or bank cards. And then you can go to them and start this collaboration. Right? So this was really in the early 1980s. So just to make it very, very explicit, what are these things? As I said, in complex dimension 1, it's just the surface of a donut. That's it, right? However, so what would the story be here? If you compactify string theory on the surface of a donut, this will give you a 10 minus 2-dimensional quantum field theory, right? That's an 8-dimensional quantum field theory, and we certainly don't live in 8 dimensions as far as we know. 8 large dimensions. Okay, let's go on. Let us look at complex dimension 2. It turns out there are exactly 2 of these things. One of which is the 4-dimensional generalization of the donut. My kids will love this. Right. That's a lot of donuts to eat. And there is this thing called the K3 complex surface, which is another classical object studied by the German School of Mathematics. But it's still not good enough, because if you compactify string theory on one of these suckers, you will get a 10 minus 2 times 2, which is a 6-dimensional quantum field theory, which is still not good enough because we don't live in 6 dimensions. We live in 4. As far as we know, we live in 4. And I can even talk to a CERN experimentalist, and we're okay. We don't get red in the face. It's okay. We do live in 4 dimensions. So we are looking for complex 3-dimensional objects, namely 6 real-dimensional things. 3 times 2 is 6. So I've got to look for these things. Well, here's a very beautiful and curious fact of mathematics. This sequence goes as one of them in dimension complex 1, 2 of them in complex dimension 2, and you would expect there are 3 of them in complex dimension 3. It is just what it is. So far, we have found 473 million of these things, at least. So it's a curious sequence in mathematics, but at least it is a conjecture of Yau that this number is finite in every dimension. So it is light, but it is the one that we want, because we want to study 6-dimensional manifolds, and yet it's just a very, very badly behaved fact of mathematics that this sequence goes as 1, 2, something at least 500 million, and the next number is at least several trillion. We don't know what it is. But this, okay, so at that point, we were, so I'll give you a bit of background as to this problem. So how do you actually construct these suckers? Right, this is a very difficult problem. How do you actually, I can construct the surface of a donut pretty explicitly. Just go to your local bakery. But how do you actually construct 3 complex dimensional manifolds? What branch of mathematics that does this? Well, there are a lot of branches of mathematics, as I said here, summarized in this table, that all do more or less this kind of thing. So, in particular, one branch of mathematics specializes precisely in this problem. And this is a branch of algebraic geometry. So somehow, this is what I grew up with, which is sort of an interface of theoretical physics and algebraic geometry. And it's just kind of curious that algebraic geometrists and physicists weren't really talking to each other until the 70s and 80s because of this curious coincidence. Of course, this sounds like a very sophisticated subject. If you're French, algebraic geometry is very hard. But if you're Italian, algebraic geometry is very easy, in a very precise sense. The French school of algebraic geometry is very, very abstract. But somehow the classical school, the Italian school of algebraic geometry is very explicit. We have all been doing algebraic geometry since kindergarten, because we all know that this is the equation of a circle, right? We were taught in kindergarten that this is the equation of a circle. That's it. What I've actually defined for you is an algebraic variety in R2. Of course, this is a very, very sophisticated way of saying this, which I highly encourage my children to do in first grade. When you're given a circle, you say, well, this is the vanishing loci of this particular polynomial. She has impressed her teachers, but probably not her friends so much. But we do one more thing, which is, I won't get into the details of it. This is the vanishing of a real polynomial, the locus of a vanishing real polynomial of dimension 1. So this is a 1 polynomial in real dimension 2. So 2 minus 1 is 1. So this defines a 1-dimensional real object. And we know the circle is a 1-dimensional real object. But we want to do a little more. We want to complexify, because we're dealing with complex manifolds. So, and we do one more thing called projectivization. This is not so important, but what we would really do, I'll just give you an example. Here's a complex equation, polynomial, in 3 projective variables. So the overall dimension is 2 complex dimension minus 1 defining complex polynomial, leaving you with 1 degree of freedom, 1 complex degree of freedom, and that is the 1 complex dimension of the surface of a torus. Okay, so let's just keep on playing this game. And it turns out that Calabi-Yau manifolds are just degree n plus 1 polynomials in CPN, if you want, for the mathematicians in the audience. Okay, so what's all this got to do with physics? Well, this became a very, very early challenge from physics to algebraic geometry, in particular string phenomenology to algebraic geometry. And it is, can you construct for me a Calabi-Yau threefold, this Calabi-Yau manifold of complex dimension 3, which has Euler number, this Euler number that I defined earlier, plus minus 6. Why? Because 6 divided by 2 is 3, and 3 is the number of generations of particles. At least that's the number that CERN tells us. Right? So this is a very, very curious thing. So we have something very, very physical. We know there are 3 generations of particles, of fundamental fermions and everything else. And I know that if I compactify string theory on any one of these spaces, I have to reproduce these 3 generations of fundamental fermions. And this translates to this very precise algebraic problem in algebraic geometry, is that can there exist Ricci flat, complex, Kähler manifolds in complex dimension 3, which has Euler number plus minus 6. This is a beautiful collaboration between 2 fields which would otherwise never have talked to each other. This is the reason why I do string theory. So, Yau's proof of the Calabi conjecture in 1978 was famously mathematical in the sense that it was non-constructive. It showed that such spaces exist. This is the ideal situation for mathematicians. It exists, but I have no idea what it is. Right? And they will never bother to actually construct an example. So physicists actually took this job of actually doing it. This is quite remarkable because, in a sense, the Italian school, classical Italian school of algebraic geometry, after Grothendieck and his French school started abstracting all of this, nobody started doing examples anymore. But then somehow physicists took back this challenge to construct explicit examples in algebraic geometry. So the first ones were with this one. This by Philippe and friends. But this is not me. This is not even. I mean, I was still in primary school then. This is Amin He, and they were doing in the early 80s on constructing various data sets. And just to give an example, I mean, I won't get into the details. The first data set that was constructed in 1986 was called the Sissies. It's a beautiful name, and these are just configurations of matrices of multi-degree in products of projective spaces. So this early example that I showed you, what I'm trying to say here is you can encode the data of in algebraic geometry at least of these manifolds into just matrices in many cases of positive integers which encodes the degree. So for example, a circle is a degree 2 object in R2. Your torus I just showed you is a degree 3 object in CP2, etc., etc. So you just keep track of this number. So you have some kind of configuration matrices. So it was realized even back then, to classify these manifolds, you need to classify these configurations of matrices. And it was already realized at that time that this problem was so difficult for the then available technology in computers that they had to turn to the best computer that was available at the time, namely the CERN supercomputer. You can ask Philip about all the stories about this. And in the classifications, you classify 7,000, about 8,000 of these manifolds with certain distributions of Hodge numbers. And and this went on in the mid-90s. Another 8,000 was found of these manifolds with certain properties. And this entire program really culminated in the 1990s and 2000s by Kreutzer and Schaka, who really bit the bullet. And I won't get into the details of this. They ran 6 months on a machine, on the dual Pentium SGI machine, which I'm sure every single student here has completely forgotten about. Even this is before my time. I mean, I vaguely know what a Pentium is as a child. But they really ran this, and they found 500 million. You think about this, 500 million of such manifolds, even by today's standards, is respectable big data, right? But back in the 90s, that's just quite unthinkable. But it's a tour de force of combination of geometry, computer science, and physics. And so they found this data. So this is all in the course of about 2 decades of a very specific problem, which theoretical physicists undertook to try both to solve a problem in string compactification and string phenomenology, particle phenomenology. But at the same time, it was tremendously helpful to the pure mathematicians because they don't bother writing down examples, right? So it was really a nice dialogue. So this is something I rip off the internet. The age of data science in mathematical physics and string theory is not as recent as you think as the last puff. That really took off in the past 5-10 days. And of course, when I got into this machine learning thing, and I tell my friend Alan, who sadly has college tutorials to do, is that, well, I'll be getting into this machine learning. Alan Barr, whom many of you know, and he says, oh, but we've been doing this for like 30 years at CERN. I was like, oh man. But it is what it is. But at least in theoretical physics and in string theory, this is a bit new. But data science in string theory and data science in mathematical physics and pure mathematics is earlier than you think it might be. So just to summarize, and here's a shameless advertisement of my upcoming book. Over 20 to 30 years of collaborations, various huge collaborations. Huge by theoretical physics standards means more than 5 people that would be working on this just to mine this data of geometries, this entire space of geometries. So here's a plot of a distribution of the Hodge numbers. So the black and white version of this plot can be found in Philip's office, framed. It's a beautiful plot which Philip and friends and Kreutz in Chicago have been drawing in the early days. My only contribution to this diagram was inspired by my 4-year-old, is I colored it in. I took the log density distribution of all known Calabi-Yaus on this plot. So you can see the red ones are very, very concentrated. I can spend an entire hour just talking about this picture, but I won't get into it. Basically, left-right symmetry of this is mirror symmetry. And here's a plot of these Hodge numbers, this topological invariance that I was referring to earlier. Right. So let's summarize. So if I compactified on each one of these Calabi-Yau threefolds, plus all of the extra data, gives me some kind of 4-dimensional universe, the geometry of which translates and then determines the particle or the particle phenomenology or the physical phenomenology of the world. This is a beautiful thing. Just to completely home in on this, right? I have a theory of quantum gravity in 10 dimensions, which works, but the caveat is that it's in 10 dimensions. I choose some geometry, I get a 4-dimensional universe. I choose another geometry, I get another 4-dimensional universe. Then I just look at it. Is this universe anything like our universe? Right? You could have, if it's got 15 generations of fermions and 70,000 Higgs particles, that's probably not something that I want to study so much. But you can from a mathematical point of view. And then all of the properties of the underlying particles, the masses, the interactions, the Yukawa couplings, and the whole lot, would translate to very, very specific problems in algebraic geometry. So this is a very beautiful fact. So for example, if you want to study the particles interactions, you have to go to this branch of algebraic geometry called cohomology theory, which I alluded to earlier. If you want to study the masses of fermions, that translates to studying the metrics. If you want to study Yukawa couplings, you do triple intersection theory on the manifolds. But everything's really nice, right? So, I've been spending my entire life jumping back and forth just to do this translation, which is extremely good because at math conferences, I can tell them I'm a physicist. And in physics conferences, I tell them I'm a mathematician. So my ignorance is always well covered. But this paradigm and this work of translation is turning out to be extremely fruitful since the 80s and 90s. And I can't help but to resist, but to quote Kepler, he famously said that where there is matter, there is geometry. And this kind of the ultimate geometrical theory is a very good vision of what string theory is, and it's the reason that I do string theory. And of course, in this choice of universes, you can take 3 possible philosophical views. Again, it's as you like. One is our universe is possibly probabilistic and anthropic within the possible space of geometries. Another view is to take that our universe is actually very, very special. That it's very hard to find the set of geometries that produce something that's akin to our universe. Or 3, you can take the completely quantum mechanical view that we are just one of all possible multiverses. I'm completely agnostic in these 3 philosophies, but I lean towards 2 whenever I'm talking to Philip. And I lean towards 1 when I'm talking to Andre Lucas. And when I'm talking to myself, actually, I don't know about the theory. I won't make any comments about the third one. But something that reminds me of this is that this is very much in spirit to the exoplanet search. Right? In exoplanets, you're looking for habitable zones within trillions and trillions of galaxies, of trillions of things, and you're looking for something that's just right. Just like what this field has in string theory has been doing is to sift through the right geometry to look for something that's just right. A universe with 3 generations of fermions, 1 pair of Higgs particles, etc., etc. So that's kind of nice. And also it's extremely good at a party when you say, hey, what do you do? I engineer universes, which is kind of a cool thing to say. So a lot of progress has been made over the last 20 to 30 years. First of all, is it even possible? If you can just start doing some no-go theorem and prove that no such geometry could ever give a universe like ours, well, no, at least, that's it. Kill off 500 million manifolds in one go, right? And then focus on another data set and try to kill that. Fortunately and unfortunately, it is actually possible. So, for example, in these collaborations, in 2005, you can actually find the exact, I have to say supersymmetric, version of the standard model from the string compactification on a very specific manifold. So it is possible to get the exact spectrum with no crap. So at least there's no no-go theorem that's obvious. And so I actually believe that there is this very active group here in Oxford that I've been working with over the years. It's just, let's just bite the bullet. 500 million is not bad, hundreds of millions is not bad. They just go sift through and they just hit one by one, and to see whether you produce a universe that's something akin to our universe, and keep going. And this program really culminated in this paper in the early 2012, which is about 200 in 10 to the 10 has the exact standard model spectrum. So 1 in a billion. So, okay, you've got crazy number of possibilities, but 1 in a billion chance that you're going to hit a universe which is something at least akin to our physical observed generator. This is no masses have been computed yet, right? Mind you, I just want to emphasize, this is just the particle content, because in order to compute the masses and your color couplings, you need the Calabi-Yau metric. And Yau's proof was famously non-constructive. He did not give us how to construct a Calabi-Yau metric. In fact, not a single metric is known beyond the trivial cases of the torus. Not a single compact Calabi-Yau metric is known. This is the power of algebraic geometry. You can make very, very strong claims without a single example. But it's sad. It is what it is, and we don't know of a single explicit analytic metric. So if we had that, it would be great. We can start computing your color couplings, but not quite yet. But just on a matter of particles, 1 in a billion or so. But then if you do some kind of extrapolation, as I was doing with Andre and Andre, even within our data set, you can get at least a mole of exact standard models just on particle spectrum. So it's quite a bit. But nevertheless, it is still possible. And this is a diagram taken from an early paper with Philip and Xenia and Balash. Is that is it possible that this funnel shape has some kind of a selection rule for special universes? But that's technical. I won't get into that so much. Meanwhile, while all of this is happening, remember this Kreutzer-Skarke program really ended went up to the early 2000s. So now we're in this century. But this century saw a complete new explosion in string theory. D-branes, M theory, G2 manifolds, F theory, fourfolds, ADS-CFT, flux compactifications, and this just grew. Instead of shrinking the number of possibilities to compactify string theory, it grew exponentially and double exponentially. There are many, many more possible solutions to string theory. So just to summarize there, this is the problem that string theory faces, which is called the vacuum degeneracy problem. This diagram I ripped off from here because it's such a nice summary of, these are all the dual and equivalent descriptions of string theory, and you can compactify all various dimensional manifolds. But the problem is, how do you choose the right geometry? Because each geometry will give you a different candidate universe in 4 dimensions. So, string theory, in some sense, for me personally, it's traded a very hard problem, namely the quantization of gravity, which every physicist thinks about, by another very, very hard problem, which is trying to find the right geometry. And to me, Well, the first one is essentially solved, but it was solved in high dimension, right? If quantization of a theory of strings happened naturally in 4 dimensions, we have nothing left to do. But it just so happens, if you wish, it predicts that this unification happens in 10 dimensions. But that's not the point. For me, this is a much more interesting problem. And the problem is that it's traded this hard problem for a problem of classifications of manifolds and classification of algebraic varieties. And I think that's a much richer problem to explore, because you get in all kinds of interesting problems in mathematics. Just to give you a ballpark, even back in 2003 and 2005, Douglas and Denev and Katru, Trivedi, okay, gosh, I'm going to try to remember all their names. Katru, Kalosh, Linda, Trivedi were estimating this famous number, which you may have read about in the press. It says that at least 10 to the 500 possible candidates to string theory. Right, so that's a big problem, and this is a kind of geometrical problem we're faced with. So but nevertheless, okay, you can try to do at least data set at a time. Just try to see what you can do. So, there've been growing databases and algorithms in collaboration with computational algebraic geometers. Now, these are the people who actually like to do examples. So these are various software that's available that you can do this, especially Sage is a wonderful thing. Sage and Macaulay 2 are wonderful things. And these databases are completely freely available online. So they're on the order of about 5 to 6 gigabytes of data. So if you're really bored tonight, go to any one of the websites, just type in Calabi-Yau or whatever G2 manifold database and just start staring at them. They are free, and just if you find it hard to go to sleep tonight, but you can just look at them. But nevertheless, the archetypical problem, because we don't have metric, is to appeal to algebraic topology and algebraic geometry rather than differential geometry. And the typical problem, no matter, these are not important, but the idea is, if you actually want to compute this kind of problem, do this translation between the geometry and the physical universe, you have to, go hardcore and study all kinds of hardcore mathematics. But nevertheless, the typical problem in string theory so far, at least in this string theory algebraic geometry interaction, is you have some kind of integer tensor input and you want to compute some integer output. So let's just digest that for a little bit. What do I mean by that? Well, a typical entry, a problem in string theory, would be, well, I give you, see, here is a Calabi-Yau manifold called a SISI, which I think is Philip's favorite thing. And then I was working with Challenger there as well on the SISIs. It's a beautiful, they stand for complete intersection Calabi-Yau manifolds, if you wish, to the deck, but it sounds like some name that you can really get acquainted with. You input this, and you want to compute topological invariance. And this topological invariance actually means something in the physics. For example, the number of generations of particles, right? But as far as the computation is concerned, you take one of these and you output some integer. And this can be helped with the help, with the introduction of any number of these very state-of-the-art computational algebraic geometry programs. So I highly encourage, and all of them are free. Unlike Mathematica, they're all free. You can download all of them onto your laptop and start playing and just data mine these databases of things, which I do all the time, which is it's a lot of fun. You're never bored because there's a lot of there's a lot of things. A lot of them are written in Python. So where do we stand? The good thing is, in the last 10 to 15 years, as I said, there is this landscape of data, right, which is more or less untouched by anybody except this relatively small community of theoretical physicists and algebraic geometers. The bad thing is the generic computation here is very, very difficult. Anything you get into any of the details, dual cone algorithms in toric varieties, triangulations of polytopes, or the Grosvenor basis computations, all of these computations are at least exponential running. So in other words, I've got 10 to the many, many possible geometries, and I've got to take this sucker and I'm trying to put it in the computer, and each running time is exponential. Right? So we'll take if you want to just do the brute force search, even within the Calabi-Yau framework of string compactification, you will take the age of the universe many times over before you can get into a tiny corner of the sift through. This is kind of nice. It's just like looking for exoplanets. It's rare. I know Sarah is an expert on exoplanet search. You can ask her about whether this analogy is perfect or not. Okay, right, okay. But what I'm trying to say, we're not going to do this, right? So the good thing is that our data is freely available, and it contributes both to theoretical physics and to mathematics. The bad is that if you want to do any of these suckers, it's exponential running time. And, well, there's the good and the bad and the whatnot. You can try to borrow new techniques from the data revolution, which only took off in the past 5-10 years. So here's a wild question. Well, if the typical problem in string theory and algebraic geometry is turning the process of an integer tensor input into some kind of integer output, why bother calculating anything at all? Right? So what do I mean by this? So a natural question to ask is that, is it possible that classes of problems in computational algebraic geometry, can it be learned by AI? After all, so far I haven't mentioned machine learning, but this is where machine learning meets physics. So in other words, can we machine learn the landscape of string theory? So I experimented with this, and it seems remarkably possible that this is doable in many situations. And interestingly, 2017 was a very good year for the field because, 4 independent groups, actually of my friends, were all thinking about the same. Things tend to be in the air. And it was only afterwards that, well, I didn't know you were working on that kind of thing. So we're even better friends now. But let me just make an analogy. So a typical problem is handwriting recognition. So this is how I write 1 to 0. Now, if you ask a mathematical physicist, how does a computer recognize from 1 to 0 here? He or she would just say, well, I'm a mathematical physicist. I can find clever Morse functions, and I can use algebraic topology. Let's scan through, and let's see how many critical points it hits in these numbers, right? That's an extremely inefficient way to try to distinguish numbers. But it's doable. It's, in theory, absolutely doable. There's a bit of variation, but that's how a mathematical physicist will usually approach this problem. But what does your phone do? Your phone doesn't do that. Your phone just takes the NIST database, and increasing every time you type in something, Google will get that data from you, like it or not, and then just starts to do this kind of association rule, right? This 6 is a 6, this is an 8, and then apply machine learning. You train it on some data set, which is augmenting ever, and then try to do this association rule. But isn't that perfect? Because a neural network doesn't know about algebraic geometry, and here's a problem that's exactly the same type. For example, if I were to tell you that this is a CC configuration, the details, okay, if you really want to know the details, this is the complete intersection of 8 hypersurfaces in complex projective space, P2 cross, whatever. Right? That's one manifold, but it's encoded into this multi-degree data. And I want to compute its Hodge number, and it turns out this number is 8. Okay, if you want to do it the proper way, this is how you do it the proper way. You sequence chase until you're blue in the face. And believe me, I've been doing this all my life, and I don't want to do it anymore. I'm crying. And then this is what Grothendieck has taught us to do. If you give you some algebraic variety, there is all the sophisticated theorems in algebraic geometry, Hodge decomposition, Euler sequence chasing, non-exact sequencing cohomology, you name it. This entire thing, this machinery, thank God, at least a lot of this has been programmed into Sage and Macaulay too. In fact, a lot of it. And then you can type in this configuration. But unfortunately, even in Macaulay 2 and Sage, the running time is exponential. So you can do it on, this computation can be done on the quintic in a matter of seconds. But if you want to do the manifold I just showed you, it will take, I don't know. There are 2 types of computations in mathematics, right? One, you can go have coffee and come back and have the answer. One is that you have to come back until the universe is died. So this happens to be one of those because it's double exponential running. So this is, and it's doable. At least, Grothendieck and friends and Laude and these people have taught us this is the proper way to do it. And luckily, people have done this computation, these for hundreds of thousands of examples, tens of thousands of examples. So as far as the machine is concerned, all it is doing, this is perfect, right? Instead of doing this hardcore sequence chase, it's just associating this configuration, which I can translate to this image, and now I'm just learning it as if it were a digit. Okay, bypassing everything in between. Everything, all of the mathematics is gone except an association rule. So you do what machine learning people do. this is great. This is how I learned about all of this subject, because 2000. So why 2017? Because in 2017, Mathematica 11.5 came out, and Mathematica 11.5 had a built-in neural network. And just because our field, this community, we're very much in love with Mathematica, even though they charge us a fortune every year for the license fees, but still, but it is what it is. And just so now it's very clear what you need to do. You train a neural network, and at the time I used a very, very simple thing, the multi-layer perceptron, which apparently is like, oh my god, you use one of those things? It's like so passé, man. Get with the times. So then I got into like support vector machines and other things a little more sophisticated, and valid against this Hodge number calculation. So then and it's good. It's giving over 90% accuracy at very low cross validation ratio. That's actually extremely good. And of course, the machine has absolutely no idea what it's doing. So then I did it properly with my student Kieran Ball here, who graduated and moved on to higher things, and also with Challenger and Vishnu, which is wanting to mention that Kieran, who is a master student here, this guy eats 50,000 lines of Python for breakfast. So he would not do this on Mathematica. He does it on TensorFlow like every other respectable human being. And then he was able to actually predict and completely classify the Hodge number computation. So here are just comparisons of neural classifiers, neural regressors, and support vector machines. And you can see that at 40% training, you're already at 80%. The point is that without going through that entire machinery of algebraic geometry. Why? I have absolutely no idea. All I know is that you have seen thousands of examples, and then it's really predicting what a Hodge number computation should be doing. Why stop there? Let's just go crazy, right? Can AI learn fancier things, like can it distinguish elliptic fibrations? For mathematicians in the audience like Mignon, this means something, and the flip. But for others, this is a hard problem. You have to there are a lot of hard theorems and conjectures that you would have to bypass in order to do this. So I was doing this with Sanjay Lee at CERN, and then look how good it's behaving. Right? At 30%, it's almost 100% accuracy in distinguishing whether a manifold is elliptically fibrated. Well, this is of interest both to the physics and the math community, because in physics, you may have heard that F theory is entirely defined on elliptically fibrated manifolds. For mathematicians, this is just crazy. It's very hard, this O'Grison-Colline-Wilson theorems, or conjectures even, and then somehow, just by looking at enough examples, you're bypassing this. Curious. So there are more success stories. Fabio Rolla, who's unfortunately not here, he did this genetic algorithm for bundle cohomology. So this is kind of really fun. You would never, prior to 2017, you would never see a preprint on the archive that combines the word genetic algorithm and bundle cohomology. These are two different worlds, right? But that's fine. We're used to this sort of thing. In 1980, the word Ricci-flat and particle physics were in two completely separate categories. They would never have talked to each other. But now they do. And now here's another very nice example, was by Andre Lucas, Andre, and Calum, and I think Rihan probably as well. Sorry, Rihan Dean should be in here. I apologize. And what they're doing is something that's very beautiful. Is that here I'm just mucking about, right? I'm just trying to guess it to 99% accuracy and whatnot. Once you hit 100% accuracy in some prediction, that's a conjecture. Right, here's a formula that mathematicians have never seen before, and here's the machine just mucks about and predicts something. Go prove it, and you actually did prove that, and that was a correct formula for bundle cohomology. This approach has never been taken before in the history of mathematics. Well, in the following sense, what is the best neural network of the 18th century? It's the brain of Gauss. So mathematicians have been doing this for a very long time, but it's just that we now have many neural networks which are far inferior to the brain of Gauss, but we have trillions of them available. And just to keep going, this is an early, last month I was working with Anthony, I think he was here, and Bert Overett, and I said about this thing about metrics, right? Yau's proof is famously non-constructive, so he's given us all of these wonderful theorems about Calabi-Yau geometry, but he hasn't given a single metric that we can use to compute Yukawa couplings. But thank God, Donaldson, who's another Fields medalist, actually came up with a relatively fast, efficient numerical method of finding these metrics, which should be used, of course, to start computing Yukawa couplings and masses. But that again is it's relatively fast, but again, it's exponentially running time. So perfect problem. So we use machine learning to, in fact, this is just a simple gradient boosted decision tree on this problem. And it was already improving it by almost 2 orders of magnitude faster in terms of actually getting the numerical metric. So that's kind of nice. So the point is, algebraic geometry over the complex numbers seems to be a very good field of study that's amenable to machine learning. Because the core computations of this subject comes down to Grosvenor basis or syzygies, whatever it is, all this fancy stuff that from the French school. It just comes down to some kind of sequence chasing of integer kernels and co-kernels of matrices, which is exactly what AI is good at. So somehow this field is good. So then I got inspired in thinking, why stop here? Why? I mean, this motivation came originally from string compactification, but there are lots of databases out there in mathematics, so we can just data mine. We've been given a hammer, and let's just like smash around and see what happens. But to echo Peter's wonderful talk in the beginning, where he did a flow chart of his life, if you were here for the first talk. This is kind of interesting. I did a similar flow chart of sort of progress in string theory. The first strings conference was in '86. The first string phenol conference in 2002. It was actually here in Oxford. The first string vacuum project, where people tried to address this degeneracy problems in seriousness, was this NSF grant from this period that was involved in. And then the first string math conference in 2011. And then the first string session at the SIME conference that at least I helped Heather Harrington to organize. It was 2014. And then 2017 is the first, there's a new series called the String Data Conference. Which is kind of interesting to see where this field is trying to, where this community is trying to go. But okay, that's enough about string theory, which is just in terms of why stop here, right? This is a question that Gukov asked in his beautiful talk a few weeks ago, when he was wondering what structures of mathematics can be learned. So here's at least some experiments that we can do. So why stop at string theory and geometry? So here I recruited Min-Young Kim, who is a very famous number theorist. I'm so honored that I'm getting number theorists to do this sort of thing. And then Min-Young actually asked me this question: when is the Latin square, or the Sudoku, the multiplication table of a finite group? This is a problem of complete technical interest to pure mathematicians. So Sudokus, right? Like one every corner, but but not every finite group can be uniquely defined by Sudoku, but not every Sudoku is a finite group. So and how to pick out one is actually not that easy. There's some theorem, but it's computationally very difficult. So we played with the support vector machine, and you could get 95% accuracy just to picking out this thing. And more wonderful problems. Another hard problem is in finite group theory is if I gave you a finite group, how do you know it's a simple finite group? And this is one of the core problems in mathematics. And here, you need fairly sophisticated things like Sylow theorems and Noether's theorems that we were taught in undergraduate second year, and then we're like, oh my god, I don't want to think about this ever again. Well, the machine doesn't think about that, and it's giving you even at 15% training, 20% training to over 95% accuracy just to test whether something is actually a finite simple group or not, which is kind of interesting that it's doing that. I have no idea why it's doing that, and I will make more comments about this shortly. How am I doing on time? I'm okay. Oh, perfect. Oh, wonderful. Now the fun begins. Why stop at the mathematics? So we've got this new tool. Let's just go crazy, right? So there's this thing. So this is a paper that I wrote again with Jajala and Brett Nelson from Northeastern. There's this thing, this neural network called Word2Vec, which some of you might have heard of. This is a purely natural language processing neural network. I won't get into the details of it, but the idea is that if I gave you a sentence, if you just do word frequency, it's not good enough, right? You can't distinguish. Well, maybe you can distinguish Shakespeare from Joyce, but you'll probably not be able to distinguish Shakespeare from Spencer, right? But the idea is how distant are words in a sentence will give you that extra mileage to try to distinguish this. So this was done by Mikolov in 1913. It was very quickly, he was grabbed by Google, made a fortune. And Google uses at least the first version of the Word2Vec. This is why, predictive testing, when you type in Google, even before you finish your whatever the hell you're trying to search for, it's already predicting the next few words. This is exactly using some variant of this version of Word2Vec. So it's fine, but for physicists, it's just it's so simple. It's just this partition function, if you wish, and we just have to minimize this partition function over text, over training text. So you should just distance, and you find some window, and you find the distance running space. Okay. So what we did is we took all 1 million titles of HepTH, HepPH, GRQC, MathPH, HepLattice, because these are sort of like relatively related fields, from the beginning of the archive in 1989 until the end of 2017 when we were working on this paper. Just to give you an idea, the word cloud of these fields are not that much different. You would expect the most common word in HepTH is the word model. Fair. The most common word in HepPH is also model. And the word in MathPH is also model. This is getting pretty boring. GRQC is black hole. Okay, bit more than model. And lattice QCD is lattice. Okay, but I won't be able to disclose. Dark matter comes up, quantum equation, quantum black hole. It's kind of interesting. You can just stare at this for a while and have fun with it. But so word cloud is indicative, but not sufficient. So of course, Ginspark has been doing some version of this. I wouldn't want to really step on his turf, but what we really want to do, we really ought to do, this is just, we did just the titles. I want to emphasize, we just downloaded the titles as a single sentences. Of course, we'll do abstracts and full texts in the future once I get enough people power. This is when Dan Friedman, who was an old professor of mine at MIT, he said, this is a problem perfectly adapted to multiple rooms of parallel processing graduate students. So just by running Word2Vec on this archive, just on the titles alone, you get some wonderful, wonderful results. You get linear syntax, because you're mapping these things to vector spaces, right? So you get identities like bosonic plus string theory is equal to open string. In other words, the most probabilistic word in this vector space that adds these two is open string. This is completely correct. Of course, you also, I'm cheating here. You also get a lot of nonsense, but at least these ones that caught the eye. But this is a really beautiful one. Holography plus quantum plus string plus ADS is an extreme of black hole. Wonderful. String theory plus Calabi-Yau is equal to M theory plus G2. It doesn't get any better than this, right? But of course, I'm hiding all the crap we got as well. But I think the crap would decrease and diminish if you start training on abstracts and the actual content. So at the time, I was hoping, and I was really trying to push for my collaborators. What I was trying to hope for, this is almost too good to hope for, was, can we predict the next revolution in physics this way? Right? Unfortunately, I was beaten. This paper in Nature came out in July. Somebody did exactly this to all 3.3 million published abstracts in material science, and they did exactly this exercise, and they predicted a host of new interactions just from the syntax of the abstract. These interactions, material science, no material scientists here, right? Don't offend anybody. But material science is just A plus B equals C plus D, right? This interaction looks good. This reaction looks good. This reaction is bad. And what do we do? Maybe it's a little more sophisticated, but why not? But these guys actually started predicting all these new things. And then said, would this never be measured in the lab before? Go measure. And then measure it is absolutely better than whatever they were doing before. So it's wonderful. But they needed 3.3 million. And we were only doing about 1 million titles instead of 3.3 million abstracts. Just go on. And you can also do classifications. So here's something that I love very much. So if you do Word2Vec on the 5 sections, you can more or less see so this is the confusion matrix of classification of these 5 sections of archive depending on title. So yeah, it's kind of pretty diagonal. So there is an inherent syntax to each field of what we call theoretical physics. What is more interesting is that, well, can you test this against non-science and pseudoscience? So nobody here submits to Vixra. This is a respectable crowd, so I think nobody does. Do you know what Vixra is? Right. Vixra is archive spelled backwards and consists of all the papers that have been rejected by archive. Okay, just blacklisted from archive. So you can pretty much say, I don't know, I want to be open-minded, but you can pretty much be sure that these are like, alternative proofs to Einstein's relativity and 7-line proofs of Fermat's last theorem. So this is good. And just this is, I love this experiment we did. Right? So they have their own section, high energy physics, quantum gravity, and string theory. Syntactically, they don't have a own consistent syntax, right? This distribution, for example, of course, if you try to do this the archive sections against the Vixera sections, it's almost diagonal. The words are there. String theory is there, quantum gravity is there, IDS is there, all the buzzwords are there, but the juxtapositions are just not quite the same. No self-respecting string theorist would ever write down a title such as, a new paradigm in quantum gravity and its subsequent generalizations to all fields of science. Whereas in Vixera, you very often see such titles. So this is just titles, just kind of interesting to see. And you can also test against things that are not science. Unfortunately, we couldn't download the times because they protect themselves. But the Indians are very, very nice. The Times of India are freely available as a good training source. So you can test archive against India, and you can just see the difference between science and non-science. And you can also, of course, see the difference between science and pseudoscience. Okay, which is kind of fun thing. So let me just summarize here. This is a very exciting era, I think, for both physics and mathematics, where you can use this new technology to do, for physics, you can use this as classifiers and predictors in the landscape of string compactifications, to say the very least. But in mathematics, this is also very, very interesting. Of course, we're not. So this is trying to address Gukov's question. We're not solving NP-hard problems, right? We're just stochastically bypassing the expensive steps of things like sequence chasing or something. At least we're not getting 100%. In other words, we're not trying to say that the traveling salesman problem can be solved in polynomial time. We can just say that stochastically you can guess at a lot of the time the correct solution without going through, because otherwise it would be crazy. And so something that I tried earlier was, well, there's something that's got to be very, very hard for machine learning to predict, and it's got to be the primes. Right? So this is something I want to try, and I want this to fail. Right? If some neural network can predict what the next prime number is, then this is pretty worrying. I don't know. I just feel deeply uncomfortable by this. And so I tried some initial experiments, and then I even talked to Sebastian, who's a computational neuroscientist, who told me, well, why don't you do the sliding window thing? Say like prime, not prime, prime, not prime, prime, and prime, try to predict the next one is yes or no. That's a binary classification, and you get pretty much as good as a coin toss, right? Which, okay. And more recently, I was working with two, card-carrying data scientists, Laura and Andrea, on trying to see whether machine learning. So this is sort of an intermediate problem. The Birch-Swinton-Dyer conjecture is somewhere in between analysis and number theory. How does machines do that? And here it's not as bad as primes, because primes would take 50-50, whatever. And if you want to classify things in there, it's a bit marginally better, like 51% of the time you actually get a correct answer, because it's somewhere in between. And I want to quantify this a little more. So at some level, I want to establish a hierarchy of difficulty, and that's something I think that Peter was asking, of problems, of branches of mathematics in terms of the response to machine learning. But of course, I'm no expert in machine learning, and people could come up with more sophisticated and deeper neural networks which make this work. But just from initial experiments, numerical analysis is very good. Algebraic geometry over C is very good. Combinatorics and algebra is very good. And number theory is very, very hard. So you see sort of this increasing sequence of difficulties of machine learning. Luckily, string theory is here. Right? It's somewhere between numerical and algebraic geometry. So somehow the problems in string theory, the typical problem, are more amenable. If the typical problem is like hard computation in number theory, this entire paradigm of machine learning landscape would not have worked. So my friend Boris says, well, he being a professor of logic, says, well, you're doing syntax without semantics. What is actually happening here? And at some level, I want to understand that there is a good analogy, right? I mean, we went from AlphaGo to AlphaZero, right? That's sort of a paradigm shift in terms of machine learning. And what we're doing here, we're still at the AlphaGo stage. We're doing supervised learning on patterns and trying to extrapolate and predict cross-validation. But of course, Voevodsky, before he passed away, pioneered this field of type theory in order to do automated theorem proving. In other words, is it possible that you feed in syntax, a syntactical, correct syntax of mathematics, and let AI try to generate new theorems and new conjectures? That would be quite, so that I would say that would be at the AlphaZero stage. Whether we are near that, I don't know. We'll see in the next 5 to 10 years. And interestingly, there was just a Nature paper out last week by Renner et al. On PRL that says they got this neural network called the SciNet. Sounds all very like Terminator 2-ish, but it's some autoencoder where they fed in the positions of Mars, and this network was able to actually predict that whatever this retrograde motion is better easily represented as a heliocentric model of the universe of the solar system with no other input. I didn't read the details of that. My graduate students are making them read it in more detail, but that seems like quite a remarkable thing to feed into whatever we're doing here. So to conclude, thank you very much. So I quote Sophia, and all of that happened in 2017. So this is a quite nice new era, I would say, for this kind of new collaboration. So thank you. Yes.
So the NP architectural problems that you are trying to do, are they problems that tend to have efficient probabilistic algorithms?
That's a good question. I think some of them are, but I'm not sure exactly. I think Fabi Ruller estimated that Grosvenor basis is something on the order of like traveling salesman, but not more. But probabilistically doable. Yeah. I hope that these ones are exactly this. Otherwise, it would be a bit crazy. Yeah.
For the Calabi-Yau triple, what I've done doing is like you already assume that the Calabi-Yau triple has an elliptic structure, or you are just input some data from the CC or something, and you try to determine whether there exists an elliptic vibration or not.
Yeah, so what we did was actually we took the SISI data set because that's a nice one, and we know which ones are elliptically fibered because of the work of Lara and James and friends. And then it's just a binary classifier. I just forget about all further input, and basically you're plotting a support vector machine, and it just says at least within the data set of SISIs, if you just plot these manifolds as a point cloud in this high dimension, there is this hypersurface which divides the elliptic ones from the non-elliptic ones for some strange reason. And I can even tell you the equation of that surface. The same way that I was doing with Minion, this is the same kind of question with the finite groups. You're plotting in the space of possible finite groups, and as point cloud in this high dimension, and you can find a hypersurface which separates the simple from the non-simple ones without any further input. So we don't know why there is this. It would be very nice if you can get this into 100%. Then we can go and tell representation theorists, forget about Sylow theorems and all that. Just look at this plane and prove that everything to this side is simple and everything to this side is not simple for some reason. I mean, a human being wouldn't have to 10 to the 500 thing back to it, but since the 1970s, people have tried to use the algebras, using algebra representation, try to reproduce the standard model. Is there a more generic way of using machine learning to try to say account for particle physics? There's a more general mathematical structure, not specific to string theory. Yes, absolutely. Yeah. Yes, absolutely. I think there's I'm fully blanking out a few names, but there's a group in Munich and there's a group in Utrecht now doing just model constructions, standard model constructions from various things. And there was even recently a paper out on machine learning quantum field theory structures just last month, just doing this kind of thing. Because it's at the end of the day, it's some data. And then if you want to sift through, our standard model is special. Can you pick our standard from some way? Yes, I think so. I think I don't know. Maybe someone can correct me, but I think Van der Wanke in Munich, they did exactly they were doing purely, I don't know, just sifting to look for standard model type things. Yeah, absolutely. Another interesting paper that I saw recently was, quantum entanglement. Right, this is a classical problem. How do you distinguish a quantumly entangled state from a non-quantumly entangled state? And computationally, that's again a very, very difficult one, especially when you have a number of, when your Hilbert space becomes very, very big. And some guys trained neural networks to distinguish the ones that it's again a classifier problem, and it was doing very efficiently picking out the ones that are actually entangled. For some reason, I don't know. It would be very nice. So that's why I like this paper of these two papers of Fabi Rula and also Rikan and Andre Lucas. They actually give the exact prediction of the formula to see why it separates in this way. Yeah. Sure. Yeah.
So if you find the right Calabi-Yau manifold, is it sufficient to reconstruct a standard model, or you need to put something in by hand additionally?
Meaning you have to. So you mean put what in hand? I mean, other than like.
You need some sort of experimental parameters. Like there are many free parameters that kind of.
Oh, I see. No, that's a very good question. We don't. I frankly don't know. Maybe Philip can shed more light. But for now, we just the 19 free parameters of the standard model. I'm not sure. In principle, there are geometric objects. They translate to precise geometric objects. Why this 19 could be translated to a very specific problem in algebraic geometry. But why this one? I don't know. It's a good question. But again, at some level, we're hoping that there will be some kind of geometrical selection rule, and that says, well, it's 3 generations because of this fact. That would be very beautiful.
Let's thank you again.
Thank you.